The ones we discussed in class, you guys remember? Circular orbits and elliptical orbits, right? There are some, with regards to elliptical orbits, there are some relationships, some formulas I'd like you to know, okay? And what we can do is, from the exam point of view, you guys can have a formula sheet. No proofs, but you can have formula sheet. But you'll be required to prove some of those expressions. Maybe one or two.
What is the next term?
The next term is midterm.
Oh, midterm?
Yeah. It's October 4th.
October 5th.
4th and 5th is what?
So it starts on the 5th, because that's what it says in the syllabus, or is it going to be on the 4th?
It could be either day, depending on when you want.
When will we decide that?
Hmm?
The ones I'm talking about. He said you were going to say this is going to be
We can go by what we mentioned in the syllabus.
Yeah, so it's going to be that Wednesday.
Yeah.
We're just going to take that.
You can do that, yeah. Okay. So you have this expression. Now, what is the energy equation? You guys remember the energy equation? Total mechanical energy is given by V square over 2 minus U over R is equal to epsilon. This is one of the expressions. This expression says energy of an orbit is only a function of its size. Okay. So here A is, what is A? The size on the semi-major axis. Okay.
Sorry.
So if you have, what it means is if you have a circular orbit and an elliptical orbit of size A, both of them will have the same energy. Okay? It doesn't matter what shape it is. So you'll be, as part of your exam, you'll be given.
So A doesn't vary by
Hmm?
the shape of it?
It will not vary by the shape of it. Okay? Yes, you're right. It will not vary with the shape.
Oh.
The epsilon will not vary with the shape. This epsilon, capital epsilon, will not vary with the shape. Capital epsilon will vary with sign. Okay?
I mean, that's what I mean. I'm sorry, size.
Hmm?
It doesn't vary with size, like circle, they have the same area as an ellipse. That's what it's called. Yeah.
No, it could have the same size.
Oh, that's not shape. Oh, true. Okay. Right.
So if you combine, let's call this B, let's call this A. combine A and B, you can write this as B square over 2 minus mu over R is equal to minus mu. What is 2A?
It's the major.
It's the major. Here, what is delta A? Now this is a statement of Kepler's second law. Okay. If you remember Kepler's second law, what is Kepler's second law? Anybody remembers?
All planets trees the
Equal areas in equal times. Right? So that means, if I write equal areas in equal time, that is dA by dt should be constant, right? Or in other words, you can say delta A by delta T is equal to constant. If you look at this, what is this equal to? Let's call this V. Delta A by delta T is H over 2, right? What do you know about H?
It's the derivative is 0, so the constant.
It's a constant, right? So that is what. So this is that second. Okay. So if I ask you to write the expression for Kepler's second law, you should be able to give me just that. Then you can have all of this in your formulation. And of course, we have looked at this expression as well. T is equal to pi mu. This is
The third law.
third. That is time period. The square of the time period is proportional to
The cubic.
cube of the mean distance. Right? A is generally the mean distance.
It's the orbiting time.
Orbiting time period.
Cubic. Distance.
This is another expression. This is another definition for eccentricity. It's the difference between the semi-major axis and the semi-minor axis divided by the sum. Now here,
What does that even mean?
huh?
What does that mean? Like, that's just a proof.
That's just the proof. So what you can look at, so we discussed this, right? Did we prove this?
Yeah.
And RP is equal to A into,
1 minus.
right? So if you're given this, you have just put this RA minus RP divided by RA plus RP. What is this? A into 1 plus C minus A into 1 minus C divided by A into 1 plus C plus A into 2. Right? And if you look at this is you have this one cancels. You get 2AE divided by 2A. Okay? Very simple proof. So you'll be in exam, let's say you'll be given this and asked to prove.
You'll be
Given this one and this one, this expression and this expression, and you may be asked to find this expression. All you need to do is just substitute for this here, and you cancel it. So if you look at this, this says eccentricity is the ratio of distance between foci divided by to its zero. Okay. So this everybody understands what is this? This is the major axis. The denominator is a major axis, right? RE plus RP. Everybody with me? If you look at this is the major axis, right? The denominator. This is the distance between the foci, RA minus RP. Okay.
You say the distance?
Distance between the foci.
Oh, yeah, you're right.
That is what the eccentricity. But look at parabolic orbit.
Yes, I see.
What do we know about parabolic orbit? Huh?
E is 0, greater than 0 or less than 1.
Is equal to 1.
Oh, it's equal to 1.
Right. So E is equal to 1. And we also looked at, if you look at the table, it said, what is the energy of a parabolic orbit?
1. No. Isn't more than 1.
It's 0. I gave you that table. Look at the table in your notes. Huh? On the formula sheet? Sure. Okay. So you have this one, right? What will R be from this? Your R can be written as h square over mu divided by 1 plus cosine theta. Right?
I thought it was E cosine theta.
Huh?
It's not E cosine theta?
Connect.
Oh, E is already 1.
Okay. So that is what you need to connect. Alright? And also what you know is v square divided by 2 minus mu over r. What is this equal to? E 0, right? Okay. So this implies v square over 2
So the kinetic energy is equal to the potential energy.
right. So there the potential energy is equal to the kinetic energy. We have v square equal to 2 mu over r, implying v is equal to
The square root.
root of 2 into root of mu over r. Now tell me, what is this? Just look at what this root of mu over r. We did this. Look at this. Anybody has your notes? Huh? The velocity of a circular orbit. This v parabolic is equal to root 2 into v circular. Okay. So this is a very, very important proof. So the question will be given to you. Show that the escape velocity. Now let's, before I give you the question, when you are in a parabolic orbit, you have to understand that you have escaped the gravitational pull of Earth or gravitational pull of the central body. Everybody understands that? As long as you are in a closed orbit, you are within the gravitational pull of the central body. Okay? If you go into a parabolic orbit is an open orbit, right? So once you go into parabolic orbit, you have escaped. But you have this energy equal to 0 means you have barely escaped. You don't have anything left to go beyond. What orbit would you be in if you had something to go beyond, escape and go beyond? It will be a hyperbolic orbit. Okay. So this v parabolic, the velocity achieved in a parabolic orbit is the escape velocity. Escape velocity. Okay, there is v parabolic. This is v escape as well. Now this escape velocity, you have to understand. What is escape velocity? Anybody?
Velocity required to escape the central body's atmosphere.
Gravitational pull, right? Not the atmosphere of this thing, but the gravitational pull. Okay. So the escape velocity, is it the same?
Is it the same as well?
So if you're looking at what it means is, you can try to escape from, let's say, Earth, the surface of the Earth. You can try to escape from, let's say, you go into the circular orbit, you go into a low Earth orbit and then try to escape from there. You go into a medium Earth orbit or a higher altitude and then try to escape from there. Would the escape velocity at these various stages be the same?
No.
It will be different, right? So here is a relationship which says if you put something in a circular orbit, okay, and you increase the velocity by 40%. What is root 2? 1.41, right? So if you increase, what this says is V escape is equal to 1.41 V circle. Got it? So what it says is, if you increase the velocity by more than 41%, what is going to happen? It will go into a parabolic orbit, not hyperbolic orbit. It will escape. Okay? So you're right. So if you increase it more than 41%, yes, you'll have a little bit of energy left to keep going. But if you increase it by 41%, you need at least 41% increase in speed to
You saying if you have a circle orbit, you only need 41% to make it what?
escape velocity. So if you want to go to moon, how would you go to moon? If you want to go to moon, how would you go to moon? You will not just go there, right? You will not just, it's not a straight line. You cannot go to moon by just going a straight line. Have you seen launches? If you have, let's say, you're in the circular orbit, right? And this is Earth, and this is where your satellite is. Okay? The satellite will have a velocity, correct? What velocity is this? V, let's call this V circular. And this could be this, think about this circular orbit could be this. It could be this. It could be this. The velocity in this circular orbit is lesser than this. Right? The velocity in this circular orbit is lesser than this. You agree?
No.
Why?
Isn't velocity more the closer you are to the central body?
So the velocity component itself will be, there are two components. One is a tangential component and the other is a radial component. So as you increase the velocity, you go into a higher orbit. The time taken is less because the distance traveled itself is less.
don't get it. Because, like, if you're spinning in a chair and you pull your arms in, you spin faster.
If you spin faster, what happens? If you spin
Velocity
faster, don't you
increases.
go
And then you like that, you slow down.
right? So if you spin, if you try to go faster here, what is going to happen? It's going to go out, right?
Yeah.
So that's what happens. If you try to spin this faster, if you try to go faster, it will go outside. If you try to spin it slow, if you slow down the velocity, it will come down. If you try to spin faster, if you increase the velocity here, it will go outward.
So in other words, the fast velocity keeps it from falling towards the earth.
Right. If you increase the velocity here, so how do you launch a vehicle or launch a satellite? You go straight up, right, and then you curve to get into that rocket. Okay. Here, what you do is, how do you don't have brakes in space, right? How do you slow down? You thrust in the opposite. So if you thrust in this direction, the velocity will impede in the other direction. Got it? If you thrust in this direction, let's say assuming this thing is going in this direction, thrust it like this, it will go there and it will go into a higher orbit. Okay. So I can explain to you more on that, but let's just focus on this. So here you have each of these. Let's for now assume that the V circular 1, so let's call this VC1, VC2 and VC3. Okay? So this you understand that VC1 is, assume VC3 is greater than VC2, VC2 is greater than VC1. Okay? Now how do you escape? You can escape from here, you can escape from here, you can escape from here. If you want to escape from here, well, how much would you increase the velocity by? Right, you would add 0.4 velocity, 0.4 times this velocity to go out. Got it? If you want to escape from here, you would add 0.4 times velocity. You get it?
So that means you have to keep accelerating at 41%.
You just increase the velocity. It's not like you don't have to keep accelerating. In space, what happens is if you increase the velocity, it stays increased. You understand? Because there is nothing to slow it down. So if you wouldn't just, if you want to go to moon, you wouldn't just go like this. So what you will do is, because you don't want to carry all that bulk, right? The rockets are really required to get you out of atmosphere. Once you're out of the atmosphere, relatively less velocity, relatively less thrust is required to go up. Okay? So this relationship is very important, and this could be a question saying, show that the escape velocity is 1.41 times the circular velocity. Or if you increase the velocity by 41%, you will get into escape. Alright, I have graded your exams. When do you want to look at it?
I don't know. I remember.
Alright, just give me an attendance, please.